If you're still awake and in the mood for gentle discovery, you've arrived at the perfect moment. Hello there, and welcome to Science of Sleep. Whether your day whisked you through bustling city streets or carried you into serene moments of reflection, find yourself a cozy spot, perhaps nestle into your favorite chair. Draw a soft blanket around your shoulders, and let your body relax as we reveal a profound cosmic secret. Why time slows near a black hole. Gravity, in Einstein's grand vision, is not a force pulling on objects, but the very curvature of space-time itself. Today, we'll witness how that curvature stretches and contorts the flow of time in the presence of a black hole's immense mass. Along the way, we'll imagine plunging clocks, reddening photons, and experiments both terrestrial and interstellar that confirm the strange, beautiful predictions of general relativity. If you happen to have a quiet moment and feel inclined to share, I'm curious, where are you watching us from, and what time is it there right now? Let me know in the comments below. So settle in, close your eyes if you like, and let that slow breath rise and fall, grounding you in your own steady rhythm, even as we drift toward regions where time itself refuses to tick normally. If this calm exploration speaks to you, please like and subscribe to Science of Sleep for more peaceful voyages through science's most wondrous realms. Imagine floating in the vast, silent expanse of space-time, as if drifting atop a boundless cosmic sea. The water is invisible, yet you sense its gentle currents guiding you toward a colossal, unseen object. That object is a black hole in abyss, so dense that it creates a funnel in the fabric of space and time itself. Around its rim lies the event horizon, the point of no return. Yet even before crossing that threshold, you notice something extraordinary. Your watch, once steady, now seems to slow. Each second stretches like molten honey, while distant clocks continue their steady beat, as if gravity has turned up the universe's brake pedal. But before we dive deeper, picture space-time as a vast rubber sheet embossed with a fine grid, each square representing 1 second of time and 1 meter of distance. In the absence of mass, this sheet lies flat and uniform. Now place a moderately heavy bola star on the sheet. A gentle depression appears, and nearby marbles roll inward under its pull. Replace that ball with an infinitely dense, wet black hole and the sheet plunges into a deep, nearly vertical funnel. Near the rim, those grid lines stretch apart, converting each 1 second interval into 2, then 10, then 1,000. A clock positioned there loses its regular rhythm relative to one resting far from the hole's grip. Its ticks grow long and lazy. Allow your shoulders to drop as you absorb that image. Each inhalation and exhalation, a steady pulse anchoring you even as time warps around you. Einstein's general theory of relativity captures this phenomenon with elegant precision. His field equations tell us that mass and energy determine spacetime's curvature, and that curvature in turn dictates how clocks tick and light travels. For a non-rotating black hole, described by the Schwarzschild solution, the time component of the metric tensor approaches 0 at the event horizon, infinite dilation of coordinate time. Yet proper time, experienced by an infalling observer, flows smoothly and uninterrupted. It is only to an external observer that the traveler's clock appears to slow and freeze. Now, let's shift focus to 2 synchronized clocks to see this. In action, clock A remains aboard a distant platform, ticking off seconds in calm regularity. Clock B descends toward the black hole, transmitting a light pulse every second according to its own time. Clock A receives those pulses at increasing intervals, first to seconds, then 10, then a minute until, at the horizon, the pulses stretch into silence. To Clock A, Clock B seems eternally suspended at the brink, its final moment frozen in space-time. Yet for Clock B, time feels perfectly ordinary, each second passing as usual right up to crossing the event horizon. Gravitational redshift offers another window into this strange behavior. A photon climbing out of a deep gravity well loses energy, stretching its wavelength and shifting toward red. Since a photon's frequency directly corresponds to the ticking of a clock, 1 cycle per second equals 1 Hertz. This redshift signals slower time at the source. When astronomers observe spectral lines from white dwarfs or neutron stars, they find those lines shifted exactly as predicted. confirming the reality of gravitational time dilation. Even here on Earth, we witness time dilation. In the landmark Half-Keating experiment of 1971, synchronized atomic clocks, flown on commercial airliners around the world, exhibited tiny but measurable differences compared to clocks left on the ground, differences exactly matching predictions. From relativity, modern GPS satellites must account for both velocity-based and gravitational time dilation to maintain pinpoint accuracy. Without these corrections, positioning errors would accumulate at kilometers per day. Yet gravity's grip on time varies with scale. A stellar mass black hole several times more massive than our Sun produces extreme dilation. A clock hovering just outside its horizon might tick so slowly that 1 second there equates to many minutes for a distant observer. By contrast, supermassive black holes, millions to billions of solar masses, warp spacetime more gently. Time dilation factors near their horizons may range from just a few times slower to tens of times slower. Still, the effect remains profound. Consider a pair of astronauts, A and B. Astronaut A stays safely distant, while astronaut B ventures toward the horizon. B sends a radio pulse each second. A receives those pulses ever more slowly, witnessing B's descent stretch into eternity. Scientists apply this principle when analyzing emissions from accretion disks around black holes. X-ray spectra show characteristic broadening and skewing due to both Doppler shifts and gravitational redshift, unlocking details about disk structure, black hole mass, and spin. But here's the twist. Inside the event horizon, all paths through spacetime lead inexorably toward the singularity. Time and space swap roles. Time becomes a direction you cannot avoid, dragging you inevitably to your doom. From the traveler's perspective, proper time continues seamlessly. It is only the coordinate description that ceases to progress. This profound reversal underscores how black holes challenge our very notions of causality and the arrow of time. In the coming chapters, we will delve into rotating black holes and the curious phenomenon of frame dragging, explore how Hawking radiation arises from quantum effects at the horizon, and examine the information paradox that has puzzled physicists for decades. But for now, let your breath remain calm, your mind steady each inhale and exhale, a reminder of your own unfrozen time in an unfathomable cosmos. This completes our first part, weaving together vivid imagery, experimental evidence, and relativistic principles. Allow that cosmic slowing of clocks to drift through your thoughts as you prepare to explore the next layers of this gravitational mystery. But before we venture further into the spinning abyss, let your breath slow until it becomes a gentle wave. Inhale softly, feeling air fill every corner of your lungs, then exhale as though you are releasing all tension into the silent void. That rhythm is your own proper time, changed by the cosmic whirlpool ahead. Imagine now drifting toward not a simple gravity well, but a vast celestial whirlpool, where mass and angular momentum join forces to set space and time themselves into motion. In this whirling realm, known as a Kerr black hole, every particle, photon, and heartbeat is carried along by a tide of warped space. Picture a tranquil mountain lake at dawn. Toss a pebble into its glassy surface and watch ripples expand outward in perfect circles. Now imagine that same lake set into steady rotation before you drop the pebble again. The ripples still radiate from the splash, but they spiral and curve, carried by the lake's spin. This is exactly what frame dragging does to spacetime around a rotating black hole, no matter how much thrust your ship's engines provide. Once you cross a certain boundary, you cannot hold still. The very fabric of space is moving beneath your feet. You approach an invisible shell called the static limit where co-rotation begins and then cross into the ergosphere, a zone between that shell and the true point of no return. Inside the ergosphere, no object can resist the spin. Imagine standing on a carousel that accelerates without warning as you take a step toward its center, until you can no longer keep your footing. The world outside your viewport transforms. Distant stars no longer appear as fixed points, but as looping arcs of light, each streak tracing a graceful spiral overhead. The deep sapphire of the night sky shifts through bruised plum and violet, before bleeding into a shade so dark, it feels almost crimson at the horizon's edge. As you drift closer, you cross that shimmering boundary, and your instruments register rising angular velocities and the tilt of inertial frames. Your ship's thrusters burn fiercely to resist the drag, yet they yield in the end. Even photons packets of light cannot hover. They spiral outward like sparks from a dancer's twirling baton. With each orbit, you measure time differently, depending on your direction of travel. If you align your craft's motion with the black hole's, spin what physicists call a prograde orbit, you ride a favorable current, like a sailboat catching a tailwind. Your onboard clock ticks more briskly though, still slower than clocks far from the hole. If instead, you fight the spin in a retrograde orbit, paddling upstream against an invisible current, time stretches further. Your seconds elongate into minutes. For distant observers, to see this more clearly, imagine two probes, alpha and beta, launched into identical circular paths just above the ergosphere's outer boundary. Alpha coasts with the rotation, beta presses its engines against it. Both emit a timestamp pulse every second according to their own clocks, and these pulses beam back to a distant observatory. Scientists there log the arrival times, alphas. Pulses arrive at ever-increasing intervals compared to betas, which lag even more. With each revolution, the difference grows until alpha's clock seems to race ahead of beta's by whole minutes or hours, a direct and measurable sign of rotational time dilation. Meanwhile, long before any spacecraft ever approached, mathematician Roy Kerr in 1963 solved Einstein's field equations for a rotating mass. Working alone in a quiet office in Wellington, Kerr discovered that a rotating black hole would form a ring-shaped singularity, not a point, and that around that ring lay an ergosphere, where space-time itself must co-rotate. When Kerr published his paper, the physics world was stunned. Here was the first exact solution, describing how spin would reshape space-time. Over the next decade, researchers tested his equations through numerical simulations and the study of orbits, gradually weaving the Kerr metric into the foundation of modern astrophysics. Within the ergosphere lies another astonishing phenomenon, the Penrose process for extracting a black hole's rotational energy. Envision sending a particle into the ergosphere where it splits into two fragments. One fragment dives into the abyss, carrying negative energy as measured by an observer at infinity, while the other slings outward with more energy than you initially provided. The black hole loses a bit of its spin in the process. Though this remains a theoretical curiosity, no known astrophysical engine copies it exactly. It underpins our understanding of relativistic jets, narrow streams of plasma launched along the spin axis at near-light speeds. Those jets, visible in radio and X-ray telescopes, carve glowing tunnels through intergalactic space, sculpting cosmic structures over millions of light-years. Here on Earth, frame dragging is subtle but detectable. The lens-thirring effect predicts that any rotating mass will twist nearby space-time, causing gyroscopes or satellites to precesses. The gravity probe B mission carried ultra-precise gyroscopes into orbit, spinning them in a near-perfect vacuum. Over months of measurement, each gyroscope's spin axis drifted by mere milliseconds. Yet that tiny shift matched the predictions of general relativity. Imagine balancing a spinning top on a table that itself twists imperceptibly. The success of that mission rested on years of painstaking engineering. Cryogenic cooling systems to maintain near absolute zero temperatures, magnetic shielding to eliminate external interference, and laser metrology so exact that a deviation of less than a hair's breadth was detectable in X-ray astronomy. Scientists measure black hole spins by studying emission lines from hot iron in the inner accretion disk. Iron atoms there emit X-rays at precise energies. But close to a spinning black hole, those lines broaden and skew under the combined effects of Doppler shifts, gravitational redshift, and frame dragging. Material moving toward us blue shifts the emission, while deep gravitational wells redshifted. The swirling spacetime then tilts the entire profile. By fitting these distorted lines with models of Kerr disks, astronomers deduce spin rates with remarkable precision. Some black holes rotating at over 99% of the maximum allowed by relativity. Gravitational wave. Astronomy adds another dimension. When two spinning black holes spiral inward, their combined spins and orbital precession imprint subtle signatures on the emitted waveforms. Detectors such as LIGO and Virgo record these ripples, allowing physicists to reconstruct not only the masses but also the spins and orientations of the progenitor black holes. Some mergers reveal significant spin misalignments, suggesting violent past encounters or turbulent accretion. History's a cosmic drama, written in the language of spacetime itself. But in that spiraling dance of light and shadow, the ergosphere reveals still more subtle wonders. Flickers that dart like fireflies trapped in a glass jar. Shadows that pulse with the black hole's heartbeat. And colors you never imagined, deep aubergine melting into molten indigo, veined with ribbons of ember gold that shimmer as if woven from stardust. Light curves in looping figures, leaving afterimages like phosphorescent trails across your vision. Each arc whispering the ancient memory of spacetime's first spin. Imagine 2. A future where space tourists dare to glimpse this spectacle firsthand. A passenger named Arya drifts in zero gravity within a transparent observation pod, wide-eyed as she watches the ergosphere's maelstrom swirl around her. Through her viewport, starfields unfurl into spirals, and jets of plasma paint the void. In incandescent arcs, her breath fogs the glass for an instant before clearing, and she reaches out as though she could touch the twisted fabric of the universe. Each data readout dings in her headset timestamp readings that grow ever more stretched, and she laughs, awed by how minutes aboard the pod become hours back on Earth. A temporal souvenir of her daring journey. In the next phase of our exploration, we witness how quantum fluctuations at the horizon give rise to a faint thermal glow, a phenomenon known as Hawking radiation, and what it implies for black hole evaporation and the preservation of information in our universe. Allow your shoulders drop as you carry these visions of twisted time and dragged space within your own proper time, a steadfast beacon amid the universe's most extraordinary choreography. But before we edge closer to the event horizon's quantum glow, pause for a moment and let your breath become a soft, tight inhale deeply, feeling the air spread to each corner of your lungs, then exhale gently, releasing any tension into the boundless silence. That steady rhythm is your proper timon, changed by the strange dance of particles at the brink of nothingness. Now, imagine standing on the threshold between two realms. On one side, the familiar world of matter and light. On the other, the inscrutable sea of warped spacetime and quantum fluctuation. Here, at the black hole's edge, virtual particles flicker like fireflies in a twilight meadow, appearing and vanishing in patterns too swift for the eye. Yet gravity's pull is unforgiving. At the event horizon, its strength can separate these particle pairs. One falls inward, doomed to the abyss, while its partner escapes outward, materializing as real radiation. This is Hawking radiation, the faint glow of quantum dust torn asunder by the black hole's might. Imagine tossing a handful of stardust into a still pond at night. Each mote lights up the surface, briefly before slipping beneath. That shimmer is the echo of quantum uncertainty made manifest, a delicate glow born of spacetime's restless trembling. Before Stephen Hawking revealed this secret in 1974, black holes were thought to be perfect cosmic traps. Hawking applied quantum field theory to curved spacetime and showed that black holes emit a thermal spectrum of particles, as if they have a temperature inversely proportional to their mass. For a solar mass black hole, this temperature is infinite than the background microwave glow of the universe, so we cannot observe it in stellar collapse remnants. But many black holes, if they exist, would radiate fiercely, evaporating in bursts of gamma rays. Picture a tiny whirlpool in a sunlit stream, at first invisible, then suddenly glinting brilliantly before vanishing in foam. And yet, the math behind Hawking's insight hinges on a simple ratio: 1/8 pi times the black hole's mass in natural units. In plain language, have the mass and you double the temperature. That inverse relationship means small black holes glow hotter than large ones. But deeply hidden in this formula lies a profound connection between gravity, quantum theory, and thermodynamics. The 4 laws of black hole mechanics mirror the 4 laws of thermodynamics. The horizon's area behaves like entropy, increasing or decreasing in lockstep with energy exchange, as if the black hole's surface stores information about everything it has consumed. But here's another layer. This link between area and entropy gave rise to the holographic principle. Imagine a library where every book ever written in 3 dimensions could be inscribed on a 2-dimensional wall. In a similar fashion, all the information about the 3-dimensional interior of a black hole could, in principle, be encoded on its 2-dimensional event horizon. This radical idea suggests that our universe itself might be a hologram, its deepest mysteries stored on distant cosmic boundaries. Yet the information paradox remains a riddle. If a black hole evaporates completely, does all the information about the matter it swallowed vanish too? Or is it somehow imprinted on the Hawking radiation, escaping bit by bit? Early on, Hawking argued that information would be lost, violating quantum mechanics' tenet of unitarity. But in 2005, he conceded that subtle quantum correlations in the emitted radiation could, in principle, carry information away. Imagine a whisper echoing through a long tunnel. Each faint repeat is distorted. But the original message survives, if you listen carefully. The debate continues today, driving research into string theory, loop quantum gravity, and the firewall hypothesis, a conjecture that an energetic barrier forms at the horizon to protect quantum coherence. Yet, despite its role at the universe's grandest scales, Hawking radiation finds analogues in the laboratory. In 2009, experiments with Bose-Einstein condensates clouds of ultra-cold atoms, acting as a single quantum entity, created sonic event horizons. When sound waves in this fluid flow encountered a boundary moving faster than the local speed of sound, phonon pairs separated, mimicking Hawking's process. Researchers detected a thermal distribution of phonons escaping the horizon. A whisper of the same effect, playing out in liquid helium or flowing water. Picture a river flowing over a submerged rock. Ripples upstream cannot return once they cross the crest. Yet tremors downstream carry a signature of that boundary, audible to those who know how to listen. Metaphor deepens our grasp of these phenomena. Consider a sheet of ice on a frozen lake, cracked by a sudden shift beneath your feet. Tiny fragments of ice pop free, some sliding under the frozen surface, others propelled outward like shards of light. That crack is the event horizon, the split in the quantum vacuum. The escaping shards are Hawking quanta, each carrying away a whisper of the black hole's hidden story. Let us also imagine a space, tourist perspective, in a far future when such journeys are routine. Aria drifts in a transparent pod, tethered just outside the horizon of a primordial micro-black hole, discovered by gravitational wave surveys. She watches in awe as the horizon glimmers with a soft golden haze, faint thermal glow against the backdrop of a starless sky. Each moment aboard the pod feels eternal. Hours pass in her subjective time, while clocks on Earth tick away days. She records the glow on her holorecorder, capturing both its spectral fingerprint and the way its intensity shifts as the black hole quietly shrinks. Her friends on Earth will marvel at the footage. Constellations shifting overhead in sped-up time. The horizon's glow flickering faster as the black hole evaporates toward its final burst. Long before we send tourists to glimpse Hawking radiation, engineers on Earth mastered the art of measuring its subtle cousins in particle accelerators and tabletop experiments. In one such setup, lasers create an optical horizon within a nonlinear medium, where the refractive index changes abruptly, trapping and mixing light in a region of curved optical spacetime. Detectors register a faint, warm glow of photons leaking from the horizon, temperature scales set by laser intensity rather than mass. It is a laboratory ballet, choreographed by Maxwell's equations and quantum optics, another testament to nature's unity across scales. Now let us turn back to our astronaut Beta, still orbiting a relic of stellar collapse. She watches as Hawking radiation softly brightens the sky behind her ship, each photon a quiet farewell from the black hole. Inside her suit, she feels no heat. This glow is colder than the emptiest cosmic background, but her instruments hum with data, flux rates, spectral slopes, tiny shifts hinting at the black hole's changing mass. She sighs with wonder, acutely aware that she witnesses entropy in the act of reversal. A cosmic scale running in reverse ever so slightly. Let your shoulders drop as you hold that image. A lone explorer, bathed in the gentle glow of disappearing space-time, charting the final story of a gravitational abyss. Let your breath return to its familiar cadence, each inhale and exhale, your steadfast metronome, measuring time where it remains unbent and true. In this tranquil moment, you stand at the border of the known and the unknown, where gravity and quantum mechanics entwine in their most intimate embrace. Allow this vision of Hawking radiation quantum pairs torn free, entropies revealed on a two-dimensional horizon, laboratory analogs humming with warm phonons to drift through your thoughts. Here at the edge of everything, the universe whispers its secrets in a glow too faint for the naked eye, yet rich with meaning for those who listen. Let that whisper lull you into a gentle stillness, where curiosity and calm converge, and the smallest particles carry the weight of cosmic truth. Allow yourself a moment of stillness. Let your breath ebb and flow like a gentle tide. Each inhalation and exhalation a reminder of your own unchanging rhythm amid the swirling paradoxes that follow. Imagine standing before a vast cosmic ledger, its pages inscribed with every particle, every wave, every flicker of energy in the universe. Now picture a black hole, a cosmic shredder that seems to erase every entry, swallowing stars, spacecraft, even stories, and reducing them to an inscrutable point. Yet quantum mechanics insists that information is never truly lost. It can only change form. How can these two fundamental truths coexist? In classical general relativity, the moment matter crosses the event horizon, it vanishes from the universe's record. No light escapes, no signal returns. Everything absorbed becomes part of an impenetrable singularity. This vanishing act suggests that the precise quantum state of influencing matter, every detail of its composition and history disappears forever. But quantum theory enshrines unitarity, the principle that information in a closed system is conserved. If information were truly lost in a black hole, it would violate the very foundation of quantum mechanics and undermine our understanding of physical law. To confront this paradox, physicists imagined that the event horizon is not a simple, featureless boundary, but a dynamic, information-rich surface. Picture that horizon as a vast, two-dimensional tapestry woven from Planck-scale threads, each thread carrying a bit of information about the matter that has crossed the boundary. This is the essence of the holographic principle, the radical proposal that all information contained within a volume of space can be encoded on its boundary surface. According to this view, the three-dimensional world we perceive may itself be a projection of data inscribed on distant cosmic screens. The holographic idea gained mathematical rigor through string theories, ADS, CFT correspondence, where a black hole in an anti-de Sitter spacetime is exactly equivalent to a thermal state in a lower-dimensional quantum field theory on its boundary. In that dual description, information is manifestly preserved. The boundary theory evolves so nothing ever truly disappears. Although our universe is not exactly anti-de Sitter, the correspondence offers a powerful model for how quantum gravity might resolve the paradox. Yet, another proposal black hole complementarity suggests that different observers experience different realities, each self-consistent, yet complementary. To an observer remaining far outside, information never crosses the horizon, but instead is absorbed, scrambled, and then re-emitted in Hawking radiation. To an infalling observer, the horizon is uneventful, and information passes through smoothly into the interior. No single observer sees information destroyed. This dual narrative preserves unitarity without violating the equivalence principle of general relativity, though it requires that no observer can compare both descriptions directly. But a further twist emerges when one considers quantum entanglement. Hawking's original calculation treated emitted quanta as perfectly thermal and uncorrelated, implying that no information escapes. To carry information, late-time radiation must be entangled not only with its interior partners, but also with early radiation, a subtle network of correlations that gradually releases the black hole's secrets. Maintaining such entanglement threatens to violate the monogamy of entanglement, leading some to propose a so-called firewall, a searing barrier of high-energy quanta at the horizon that breaks entanglement and preserves unitarity at the cost of a dramatic violation of relativity's smooth spacetime. This firewall hypothesis challenges our deepest intuitions. It asserts that any observer crossing the horizon would be incinerated by the firewall's energetic blaze, rather than experiencing no drama. The paradox thus forces us to choose which principle to sacrifice: the equivalence principle of general relativity, the unitarity of quantum mechanics, or the monogamy of entanglement. No consensus has yet emerged, and the debate fuels research. Across theoretical physics, beyond these conceptual frameworks, experimental and observational strategies offer potential glimpses of the horizon's true nature. Gravitational wave detectors, such as LIGO and Virgo, might capture echoes following the main merger signal of two black holes. These echoes would arise if the horizon reflects, rather than perfectly absorbs. Incoming waves each echo a faint memory of the black hole's microscopic structure. Detecting such echoes would point to a horizon that is more like a vibrating drumhead than a one-way membrane. Similarly, very long baseline radio interferometry exemplified by the event horizon telescope aims to resolve the photon ring surrounding a supermassive black hole's shadow. Tiny brightness variations around that ring could encode information about irregularities on the horizon. Pixels of quantum geometry flickering as they record in falling matter. Analyzing these substructures requires pushing imaging techniques to their limits, but offers the promise of horizon spectroscopy. Laboratory analogs provide complementary insights. In ultra-cold atomic gases, optical fibers, and flowing water systems, physicists engineer horizons for phonons, photons, or surface waves. These analog horizons emit thermal radiation akin to Hawking's prediction. By measuring correlations between emitted quanta, researchers study how information may be transmitted or scrambled at a boundary. Though these experiments do not recreate a real black hole, they reveal the general principles by which quantum fields behave in curved geometries. Another promising line of inquiry arises from quantum information theory itself. Physicists modeled the horizon as a quantum error-correcting code that protects information against partial loss. In this view, the horizon's microstates are entangled in such a way that errors introduced by Hawking radiation are automatically corrected, preserving global information. This mathematical structure hints at deep connections between quantum gravity and the architecture of future quantum computers. In parallel, loop quantum gravity offers a discrete picture. Space-time geometry, quantized into finite atoms of area, each quantum of area contributes a bit of entropy to the horizon. As the black hole evaporates, these quanta rearrange and release their stored information. Though the full dynamics remain under active development, loop approaches seek a direct, microphysical account of horizon entropy and information release. Imagine a future laboratory or satellite mission where tiny black holes, perhaps relics from the early universe, are monitored as they evaporate. Sensitive detectors could register bursts of high-energy particles and, by analyzing subtle correlations in the radiation, reconstruct aspects of the original in falling matter. Such a feat would demonstrate in practice that black holes are not information sinks but complex processors that transmute input into output in accordance with quantum law. Finally, contemplate a space station orbiting a primordial black hole of near-asteroid mass. Astronauts there measure gravitational waves and Hawking-like emissions, their instruments tuned to detect the faint whispers of quantum gravity. Each data stream feeds back to theoretical models, refining our understanding of horizon dynamics. Across years of observation, the station's crew pieces together a coherent picture. Information never truly perishes, but weaves through horizons, boundaries, and correlations, preserved in the universe's grand tapestry. Allow your shoulders to relax and your breath to flow calmly as you absorb these interwoven visions, firewalls, or complementarity, holographic screens or quantum codes, gravitational echoes, or photon ring secrets. Each idea reflects a path toward reconciling gravity and quantum mechanics, the ultimate synthesis of our theories. In this interplay of paradox and possibility, we glimpse both the limits of our knowledge and the boundless ingenuity of human thought. Settle into your seat and let your breathing find a gentle, unhurried pace. Inhale quietly, feeling the air expand your chest like distant cosmic rays warming a silent nebula. Then exhale slowly, releasing any tension into the surrounding calm. That steady rhythm is your own proper time, a beacon of continuity, as we journey outward from the event horizon into the brilliant, roiling expanse of the accretion disk, the cosmic engine fueling the black hole's hunger picture. First, how? These disks are born in a galactic core or a binary system, gas clouds and stellar debris spiral inward under gravity's pull. Tidal forces stretch and shear the infalling matter, forming a flattened, swirling pancake of plasma. Imagine an ice skater drawing in their arms and spinning faster. Similarly, as gas loses angular momentum through friction and magnetic stresses, it draws closer and orbits ever more rapidly. The result is a luminous, turbulent disk glowing across the electromagnetic spectrum from radio waves in its outer, cooler regions to searing X-rays near its inner edge. Yet this birth is rarely serene. Consider a star straying too close to a supermassive black hole. The tidal forces tear the star apart in a cataclysmic tidal disruption event. Debris streams along elongated arcs, colliding with itself to form shocks that heat plasma to tens of millions of degrees. Within days or weeks, a transient accretion disk coalesces, its intense radiation outshining the galaxy's core for months. Astronomers detect these flares in optical, ultraviolet, and X-ray surveys each light curve tracing the disk's rapid assembly and eventual fading. But before the disk settles, magnetic fields already thread through the chaos. Microscopic charged particles in the plasma generate currents, amplifying seed fields via a dynamo process. Picture millions of tiny compass needles spinning and aligning under turbulent flows, gradually building a coherent field strong enough to influence the entire disk. These magnetic fields mediate angular momentum transport through the magnetrotational instability, allowing matter to spiral inward while magnetic torques fling energy and angular momentum outward. This mechanism, first proposed by astrophysicist Stephen Balbus in the 1990s, revolutionized our understanding of disk evolution. Allow your shoulders to drop as you envision this interplay of gravity, turbulence, and magnetism, a cosmic ballet, where plasma eddies whirl like dancers spinning in a grand amphitheater. As the disk matures, it enters a quasi-steady state, mass accretion rates balance with radiative cooling, and the disk's structure can be approximated by the standard alpha disk model. In this framework, the disk's temperature and density vary smoothly with radius, cooler and denser on the outside, searing hot and tenuous near the inner stable orbit. Detailed spectroscopic observations, for instance, of the black hole binary Cygnus X1, reveal multi-temperature blackbody spectra that match these predictions. Each wavelength band a window into a different ring of the disk. Yet no disk is perfectly uniform. Localized magnetic reconnection events, so solar flares can erupt as coronal outbursts above the disk's surface, emitting hard X-rays and illuminating the disk below. Observers call this reflection spectroscopy, the X-ray. Corona acts like a lamp, and its light reflects off the disk's surface, imprinting characteristic iron fluorescence lines. By analyzing the shape and shift of these lines, astronomers map the disk's geometry, ionization state, and even the black hole's spin, since faster spins drag the disk's inner edge closer in, altering the gravitational redshift of the reflected emission. To understand how disks die back into quietude, consider low luminosity systems, such as Sagittarius A*, the Milky Way's central black hole. Here the accretion rate is millions of times lower than in active quasars. The disk becomes radiatively inefficient, its plasma too hot and tenuous too cool effectively. Instead of a cool, thin disk, you get a hot, thick torus, or an accretion flow, where most of the energy is carried into the black hole rather than radiated away. These underfed disks shine faintly, their spectra dominated by radio and submillimeter emission, the cosmic equivalent of a dying ember. But even in quiescence, disks can spring to life. Perturbations, such as the infall of a gas cloud or the magnetic reconnection of field lines, can reignite accretion, producing flares that crackle across the spectrum. Monitoring campaigns of nearby galactic nuclei reveal months-long cycles of faint flares, hinting at the episodic nature of black hole feeding. Allow your breath to flow gently, each cycle a reminder that while disks evolve over years, centuries, or longer, you remain the steadfast observer at your own steady pace. In the most dramatic spectacles, accretion disks launch powerful relativistic jet columns of plasma, collimated along the black hole's rotation axis and propelled outward at near light speed. The Blandford's Nyack mechanism, explains how the black hole's spin energy, tapped by magnetic fields anchored in the disk, powers these jets. Imagine twisting a rubber band until its stored energy flings objects outward upon release. Similarly, twisted magnetic field lines accelerate charged particles into narrow beams extending for thousands of light years. These jets sculpt radio galaxies, inflate giant cavities in galaxy clusters, and regulate star formation by heating intergalactic gas on laboratory plasmas. Tokamak experiments on Earth attempt to contain hot ionized gas with magnetic fields, closest analog to the astrophysical disk environment. Instabilities such as kink modes and edge-localized modes in tokamaks mirror the magnetorotational and Kelvin-Helmholtz instabilities that drive turbulence in accretion disks. Insights from fusion research inform astrophysical models, just as observations of distant disks inspire new approaches to confining fusion. Plasmosa symbiotic exchange across scales. Finally, consider the chemical alchemy within disks. Under intense heat and pressure, light elements fuse into heavier nuclei: carbon, oxygen, even iron before being shredded into plasma. These newly forged elements mix within falling gas and can be expelled by disk winds, seeding the surrounding galaxy with the raw materials for planets and life. In protoplanetary disks around young stars, scaled-down analogs of black hole disks, this process builds the rocky cores of terrestrial worlds. Though the physical conditions differ vastly, the underlying principle holds. Disks are cosmic crucibles, forging complexity from simplicity. Allow your shoulders to relax fully, and your mind to trace the spiral arms of this luminous disk. Each ring a chapter in a black hole's life story. Let your breath return to a natural rhythm, each inhale and exhale, your personal metronome, marking proper time. Amid the disk's grand evolution, from birth in tidal carnage to quiet embers and explosive jets, from magnetic flares to chemical forges, accretion disks embody the universe's creativity. In what follows, we will turn our attention to how these disks interact with their galactic environments, how feedback from black hole feeding shapes the galaxies themselves, orchestrating the cosmic web's grand design. Allow your breath to settle into a soft, unhurried flow. Inhale, gently letting air expand your chest, like a distant nebula unfolding. Then exhale slowly, releasing any tension into the calm that is your anchor of proper time. As we now turn from the intimate realm of the accretion disk to its grand influence on the galaxy that hosts it. Imagine jets and winds born in that fiery disk, not as isolated fireworks, but as architects sculpting entire galaxies over millions of years. Consider first how powerful outflows arise. Magnetic fields anchored in the inner disk twist under the black hole's spin, launching narrow relativistic jets that blast through interstellar space. At the same time, radiation pressure and thermal heating drive slower, wider winds from the disk's surface. Picture a cosmic garden hose spraying both a focused high-speed jet and a broad, gentler mist. These two modes of feedback carry energy, momentum, and newly forged elements into the surrounding medium, heating gas, suppressing star formation, and regulating a galaxy's growth. But before exploring their galactic scale impact, imagine a serene lake on a summer day, suddenly struck by two phenomena: a concentrated stream of water from a fire hose and a fine spray from a garden nozzle. The hose carves channels in the lake bed, while the mist cools and nourishes the shoreline vegetation. In a similar fashion, relativistic jets carve cavities in hot gas halos that envelop galaxies, while slower winds enrich the interstellar medium with heavy elements and heat cold molecular clouds, preventing runaway collapse into stars. Let your shoulders drop and rest as you envision this dual influence. Jets piercing the galactic halo like cosmic drills, and winds whispering through spiral arms like spring breezes, stirring new growth. Astronomers observe these effects in galaxy clusters, where powerful radio jets inflate vast bubbles in the diffuse X-ray emitting gas. These bubbles rise buoyantly, their edges bright with shock fronts that heat the gas and prevent it from cooling catastrophically. Without such heating, the gas would cool, condense, and form stars at rates far higher than observed. Instead, Feedback from the central black hole maintains a delicate balance. It throttles star formation and keeps the cluster in a steady state for billions of years. Yet galaxies come in many shapes and sizes. In massive ellipticals, jets dominate the feedback, carving giant cavities tens of thousands of light-years across. In more modest spiral galaxies, winds from the disk's ultraviolet and X-ray radiation drive multi-phase outflows. Imagine the difference between a powerful fire hose blasting away loose soil and a gentle breeze carrying seeds to new fields. Both shape the landscape, but in distinct ways. Similarly, black hole feedback adapts to a galaxy's mass and gas content, orchestrating its evolutionary path. Transitioning to observations, we see signatures of these outflows across the electromagnetic spectrum. Blue-shifted absorption lines in ultraviolet spectra reveal cold gas streaming outward at hundreds of kilometers per second. In infrared, we detect warm molecular hydrogen riding the wind. X-ray observations show hot, ionized gas filling cavities and streaming along jet channels. By combining these tracers, astronomers map the full ecosystem of feedback from the fastest, most penetrating jets to the slowest, most nourishing winds. Parallel insights come from cosmological simulations that incorporate black hole growth and feedback. In these virtual universes, galaxies that include only gravity and gas cooling become overly massive and blue, brimming with new stars. When feedback is added with energy injection calibrated to reproduce observed quasar winds and jets, simulated galaxies match real ones. Massive ellipticals appear red and dead. Spiral galaxies maintain moderate star formation rates, and galaxy clusters exhibit stable hot omspheres. Think of a bonsai tree cultivated through careful pruning. Without snipping back the shoots, it would grow wild and unruly. Black hole feedback plays the role of the gardener's shears, trimming star formation and guiding galactic architecture over cosmic time. Let your breath return to its steady pace. Each inhale and exhale, a personal metronome amid these vast processes. Feedback also seeds the intergalactic medium with heavy elements. Winds carry carbon, oxygen, and iron forged in the disk's high-temperature furnaces into the galactic halo and beyond. Observations of quasar absorption lines reveal metals in the space between galaxies avoidance that black hole-driven outflows have enriched vast volumes of space, planting the raw materials for future generations of stars and planets. Meanwhile, the same black hole that heats its environment during active phases lies dormant in quieter times. Yet its earlier feedback leaves a lasting imprint. Elliptical galaxies show X-ray cavities devoid of gas, relics of ancient jets. Surrounding gas remains too hot and diffuse to collapse, preserving galactic quiescence. In spiral galaxies, central winds may clear out gas reservoirs, triggering cycles of starburst followed by dormancy. A heartbeat of activity, paced by the black hole's feeding laboratory. Analogues of feedback appear in plumes rising from heated fluids, or in dusty winds in wind tunnels, where momentum transfer shapes. Flow patterns. Engineers study these flows to improve combustion efficiency and pollutant dispersion. In turn, astrophysicists adapt those fluid dynamics models to understand how black hole-driven outflows interact with interstellar clouds, another testament to the unity of physical principles from the lab to the cosmos. In the end, the story of galaxy formation is inseparable from the story of black holes. These cosmic dynamos do more than consume. They sculpt and sustain. They regulate starbirth, shape gas dynamics, and seed chemical complexity across millions of light-years. When you gaze at a spiral galaxy's graceful arms or a massive cluster's glowing halo, remember the hidden hand of feedback guiding its evolution. Allow your shoulders to relax fully and your breath to flow gently as you carry this vision within you, jets carving cavities, winds enriching space, and the black hole's hunger coordinating the grand feedback loop that shapes galaxies. Your own steady heartbeat remains the quiet witness to these majestic processes, proper time flowing onward, while the universe's greatest engines run in harmony. Allow your breath to drift into a calm, effortless rhythm. Hail softly, feeling cool air fill your lungs. Then exhale slowly, releasing any tension into the vast stillness. That steady pulse is your proper time, guiding you now into the realm where ripples in spacetime reveal the hidden lives of black holes. Imagine listening not to light but to gravitational waves, the faint tremors emitted when black holes dance, collide, and merge. When two black holes spiral toward one another, they set the very fabric of spacetime quivering like a struck tuning fork. At first, their orbital dance emits low-frequency ripples, gentle and widespread. As they draw closer, the frequency rises, the amplitude grows, and the waves become a cosmic roar, culminating in a final dramatic merger and a fading ringdown as the newly formed black hole settles into equilibrium. Detecting these gravitational waves requires instruments of extraordinary sensitivity, laser interferometers that measure changes in distance smaller than a proton's diameter across arms several kilometers long. In 2015, the Laser Interferometer Gravitational Wave Observatory first registered such a signal from two black holes, merging 1.3 billion light-years away. The characteristic chirp, a rising pitch lasting fractions of a second, matched exactly the predictions of Einstein's general relativity. Each merger waveform encodes the masses and spins of the progenitor black holes, as well as the distance to and orientation of the source. By comparing observed signals to extensive banks of numerical simulations, physicists extract these parameters with remarkable precision, opening a new window on the population of black holes across the universe. But before we delve deeper, picture yourself immersed in a vast ocean of silence, broken only by the gentle swell of passing waves. These waves carry stories of exotic events, stellar binaries spiraling inward over millions of years, massive progenitor stars collapsing into black holes that then pair up, and even the echoes of the early universe's primordial density fluctuations. When a gravitational wave observatory picks up a signal, it is as if you have dipped a specialized antenna into that silent sea, plucking out a single note from a cosmic symphony. Allow your shoulders to drop as you imagine tuning your instrument to the universe's deepest frequencies, each beat of your heart synchronized with spacetime's gentle tremors. Gravitational wave detections come in two main classes: stellar mass mergers, observed by ground-based detectors such as LIGO and Virgo, and supermassive mergers that will be probed by space-based observatories like LISA in the coming decade. LIGO and Virgo are sensitive to waves in the tens to thousands of hertz range, ideal for black holes of a few to a few hundred solar masses. These detectors consist of two perpendicular arms, each 4 kilometers long. Laser beams travel back and forth along these arms, and any differential change in length indicates a passing gravitational wave. Supermassive black hole binaries, with millions to billions of solar masses, emit much lower frequency waves to microhertz, requiring instruments in space to achieve the necessary long baselines. The Laser Interferometer Space antenna will consist of 3 spacecraft forming a triangular constellation with sides millions of kilometers long. By monitoring the distance between free-floating test masses inside each spacecraft with precision, LISA will detect the slow, majestic chirps of supermassive mergers at the hearts of colliding galaxies. Each detection enriches our understanding of black hole demographics and cosmic history. For instance, LIGO's catalog reveals a surprising abundance of black holes with tens of solar masses heavier than those expected from single-star evolution models. These observations have prompted new theories about parent stability supernova, low metallicity environments, and hierarchical mergers in dense stellar clusters. Meanwhile, future LISA observations will probe how galaxies assemble by catching mergers of their central black holes across cosmic time. Yet gravitational waves do more than reveal masses and spins. They test fundamental physics. When two black holes merge, the waveform's intricate structure, including in spiral, merger, and ring-down phases, allow stringent tests of general relativity in the strong field regime. So far, every signal has matched Einstein's predictions to within experimental error, but as detectors improve, we may uncover subtle deviations hinting at new physics, Wright bosons forming clouds around black holes, or modifications of gravity at extreme curvatures. Turning from theory to practice, crafting accurate waveform templates demands massive computational efforts. Numerical relativity simulations solve Einstein's field equations on supercomputers, tracking how spacetime bends and twists during a merger. simulating each scenario from equal mass, non-spinning binaries, to highly eccentric. Processing systems requires weeks of computing time. These waveforms populate template banks used in matched filter searches, sifting weak signals from instrument noise. Machine learning techniques now accelerate this process, interpolating between existing waveforms to cover parameter space more efficiently. Meanwhile, multi-messenger astronomy combines gravitational waves with electromagnetic observations. The landmark detection of a neutron star merger in 2017, accompanied by a gamma-ray burst and kilonova emission, demonstrated the power of coordinated observations. Though black hole binaries are less likely to produce bright light, scenarios exist such as mergers in dense gas environments or black hole neutron star pairs where electromagnetic counterparts arise. Observatories across the spectrum, from radio arrays to X-ray telescopes, stand ready to chase counterparts, offering insights into accretion physics, jet formation, and host galaxy properties. As gravitational wave observatories accumulate more events, we will map black hole merger rates as a function of mass, spin, and redshift. This census will illuminate the origins of black holes, whether they predominantly form in isolation, through dynamical interactions in clusters, or via primordial mechanisms in the early universe. Each channel leaves distinct imprints on the mass-spin distribution and merger environments. Consider, for a moment, the smallest black holes we might detect, those formed in the first billion years after the Big Bang, with masses of a few tens, 200s of solar masses. These seeds could grow via mergers and accretion into the supermassive titans we see today. LISA may observe intermediate mass black hole mergers at intermediate redshifts, bridging the gap between stellar and supermassive scales, and tracing the cosmic web's assembly. Let your breath return to its steady pace. Each inhale and exhale, your personal metronome amid these cosmic revelations. Gravitational waves have transformed black holes from theoretical curiosities to observable phenomena, objects we can hear as well as see. In the chapters ahead, we will explore how black holes influence cosmic structure on the largest scales, from sculpting galaxy clusters to shaping dark matter halos, weaving the tapestry of the universe from the smallest ripples to the grandest filaments. Until then, carry the whisper of spacetime's tremors within you, a testament to the universe's deep harmony. Allow your breath to settle into a calm, unhurried flow. Inhale gently, feeling air fill your lungs like a soft tide, then exhale slowly, releasing any lingering tension into the surrounding stillness. That steady rhythm is your proper time, your constant companion as we now expand our view beyond individual galaxies to the vast cosmic web woven by gravity and dark matter, an immense network in which black holes play a subtle, yet profound role. Imagine the universe as a three-dimensional spider's web of filaments and voids, stretching across billions of light-years. Along these filaments, matter flows like water in braided streams, feeding galaxies and clusters where filaments intersect. At the junctions lie the most massive structures in the cosmos: galaxy clusters and superclusters, each harboring hundreds or thousands of galaxies, permeated by hot plasma and threaded by magnetic fields. Yet underlying this luminous tapestry is a darker framework, dark matter halos, that provide the gravitational scaffolding for all visible structures. Within these halos, black holes reside at the hearts of galaxies, influencing not only their immediate surroundings, but also contributing to the evolution of the large-scale architecture itself. But before we trace those grand connections, picture the web in miniature, spinning droplets of honey on a fine net. Each droplet representing a galaxy cluster, each strand a highway of matter. Light travels along these highways, but gravity bends its path, and black holes embedded within the clusters act as local whirlpools, drawing in gas, stars, and even entire galaxies over eons. Their feedback jets and wind seats the intricate medium, slowing, cooling flows, and influencing how gas condenses into new galaxies. In this way, black holes help regulate structure formation from the smallest scales of star birth to the largest scales of the cosmic web. At the centers of galaxy clusters lie supermassive black holes, with masses hundreds of millions to tens of billions of times that of the Sun. When these black holes become active, They launch titanic jets that inflate bubbles hundreds of thousands of light-years across in the surrounding hot gas. Observations with the Chandra X-ray Observatory reveal these cavities as depressions in the X-ray emitting plasma, bounded by bright rims where shock fronts heat the gas. These bubbles rise buoyantly, distributing energy and magnetic fields throughout the cluster core, preventing runaway cooling that would otherwise lead to excessive star formation. Imagine dropping a heated rock into a calm pond. Ripples carry heat outward, spreading warmth evenly. Similarly, black hole jets distribute energy across vast volumes, maintaining the thermal balance of cluster gas. Let your shoulders drop as you visualize these colossal bubbles, each an echo of a black hole's heartbeat, cluster-like cosmic lungs, inhaling and exhaling energy. Beyond clusters, the cosmic web's filaments host a diffuse, warm-hot intergalactic medium, WHIM, at temperatures of 1 million to 10 million degrees. Detecting the WHIM remains challenging, yet absorption lines in quasar spectra and faint X-ray emission hint at its presence. Black hole-driven winds from galaxies enrich this medium with heavy elements, carbon-oxygen, iron seeding the cosmic web and influencing its cooling rates. Imagine a tree shedding seeds in all directions. Winds carry those seeds far beyond the canopy, allowing new growth to spring up in distant fields. In the same way, black hole feedback propagates enriched material along filaments, shaping chemical evolution on intergalactic scales. In cosmological simulations, incorporating black hole feedback transforms the universe's appearance. Without feedback, simulations produce too many stars too early, creating galaxies that are too bright and too massive compared to observations. When realistic prescriptions for black hole-driven energy injection are included, the star formation histories align with surveys. Massive galaxies quench early. Cluster gas remains hot and diffuse, and the cosmic star formation rate peaks at the observed redshift of around 2. These simulations reveal that black holes act as thermostats for galaxy formation, dimming starburst flames in massive halos while allowing smaller galaxies to form stars on more extended schedules. Now, consider how black holes themselves grow in this web. Higher redshift, quasars, active black holes, shining brightly when the universe was less than 1 billion years old, pose a challenge. How did they accumulate billions of solar masses so quickly? The rapid growth likely required both abundant cold gas supplied along filaments and episodic super-Eddington accretion phases, perhaps facilitated by dense mergers or disk instabilities. Filamentary flows channel gas efficiently into proto-galaxies, feeding their central engines. Imagine a network of rivers converging into a delta. Plentiful inflows sustain a powerful mill, grinding grain at a prodigious rate. Similarly, filaments feed the earliest quasars, powering their rapid rise to supermassive scales. Let your breath flow evenly. Each cycle a reminder that while black holes and galaxies evolve over cosmic epochs, you observe from the timeless present in the local universe. Surveys of galaxy velocities reveal the influence of dark matter and black holes on galactic motions. The tight correlation between a galaxy's central black hole mass and its bulge velocity dispersion, the M-sigma relation, suggests a coevolution. Black holes and their host spheroids grow in tandem, regulated by feedback that couples the small-scale physics of accretion to the large-scale dynamics of stars. It is as though two dancers, one small and one vast, move in step across a cosmic stage, each guiding the other's tempo. Shifting our focus to voids, the vast underdense regions, spanning tens of millions of light-years, we find that they too feel the indirect effects of black holes. In void galaxies, low-mass halos harbor black holes that rarely accrete, and feedback is minimal. Yet as the cosmic web's structures evolve, void boundaries sharpen and filaments narrow, influencing how gas flows onto isolated halos. The absence of strong feedback in these regions leads to a different pattern of galaxy evolution: slower star formation, lower metallicities, and unique morphological trends. In this way, black holes contribute to the universe's rich diversity, from bustling clusters to serene voids. Across cosmic time, black holes serve as both tracers and drivers of structure. Surveys of quasar clustering show that active black holes inhabit the densest regions at high redshift, gradually migrating into the centers of mature clusters by the present day. Their bias relative to the underlying dark matter distribution illuminates how mass assembles. Quasars trace the peaks of the primordial density field, guiding our maps of large-scale structure. Let your shoulders relax fully and your breath remain a steady metronome as you hold these grand visions clusters sculpted by jets, filaments enriched by winds, voids shaped by silence. Black holes are both consumers and creators, carving out galaxies and weaving the cosmic web's tapestry in the vastness of space. From the smallest primordial seeds to the largest cosmic filaments, we see black holes as indispensable actors. Their insatiable appetites regulate star formation. Their jets and winds heat and enrich the intergalactic medium, and their growth chronicles the universe's assembly history. When you gaze at the night sky, remember that each point of light rests atop a foundation of dark matter and black hole physics. Born in the interwoven dance of gravity and quantum laws, your own steady pulse remains the quiet witness to this cosmic symphony, proper time flowing on as the universe continues its grand evolution. Allow your breath to settle into a gentle, unhurried cadence. Inhale quietly, feeling your chest expand as though cradling the universe's mysteries. Then exhale slowly, releasing any tension into the surrounding calm. That steady rhythm is your proper time, the constant thread that weaves through every part of our journey. Now, let us turn inward once more, reflecting on how the cosmic odyssey we have shared, from the warping of time near a black hole to the vast architecture of the cosmic web, resonates within our own lives. In our exploration, we traced light, slowing and reddening under gravity's grip. We witnessed space-time spun into vortices by rotating singularities. We saw quantum dust briefly sparkle as Hawking radiation, and we pondered the fate of information at the event horizon. We mapped the fiery birth and quiet embers of accretion disks, felt the pulse of merging black holes through gravitational waves, and surveyed the highways and byways of the cosmic web, shaped by feedback from central engines. Each insight revealed layers of complexity and unity. The same rules that govern electrons in an atom also sculpt galaxies and weave the very fabric of space-time. Yet amidst these grand scales, consider for a moment your own heart beat steady, reliable, unbroken. In the face of unfathomable forces and cosmic epics spanning billions of years, this simple biological rhythm reminds us that life unfolds here. In the gentle cradle of Earth, the very atoms within your body were forged in stellar furnaces, carried by interstellar currents, assembled in a planet teeming with water and life. Black holes, acting as cosmic recyclers, have shaped the distribution of heavy elements and regulated star formation, indirectly seeding the conditions that make life possible. Imagine tracing the lineage of a single oxygen atom in your bloodstream. It might have been born in a supernova, passed through an accretion disk's jets, mingled in the cosmic web's filaments, cooled into a molecular cloud, formed into our sun's protoplanetary disk, and finally inhaled by you in a breath of Earth's atmosphere. All along that journey, black holes sculpted the large-scale environment, their powerful feedback preventing runaway star formation in galaxies and maintaining the delicate balance of elements in the intergalactic medium. Allow your shoulders to drop as you absorb that thought. Single atoms voyage across time and space, guided by the universe's grandest engines, now part of your own being in moments of quiet reflection. We often gaze at the night sky and feel a sense of wonder, mixed with calm. The soft glow of distant stars, the band of the Milky Way arching overhead, the subtle twinkle of planets. These sights connect us to the cosmos. Knowing the physics behind those lights, the nuclear furnaces, the curved spacetime, the quantum fluctuations, adds depth to our AHOA without diminishing its beauty. On the contrary, scientific understanding becomes a form of poetry, revealing unseen harmonies that underpin the visible splendor. Black holes, once relegated to the realm of theory, now stand as tangible cosmic actors, thanks to observations across the electromagnetic spectrum and the direct detection of gravitational waves. These discoveries have transformed our view. Rather than impenetrable enigmas, black holes appear as dynamic, information-rich objects with measurable properties. They twist and tug at spacetime, launch jets that sculpt galaxies, and whisper quantum secrets in the faintest radiation. In every respect, they embody nature's dual character, both simple in their defining properties and infinitely complex in their interactions. Consider how this duality reflects our own lives. We, too, have strengths and vulnerabilities, simple needs and intricate inner worlds. Just as a black hole's mass, spin, and charge determine its overall behavior, while its environment and quantum effects add nuance. Our basic experiences, heartbeat, consciousness, underlie vast layers of thought, emotion, and connection. In both cases, embracing complexity enriches our understanding and deepens our appreciation. Let your breath become your anchor once more. Each inhale a connection to the universal flow of energy. Each exhale a release of tension, a reminder that you participate in this grand tapestry. As we conclude this voyage, reflect on the tools that brought us here. Telescopes that capture starlight across billions of years. Interferometers that measure spacetime ripples smaller than an atom. Particle detectors that glimpse quantum dust, and the human mind itself, capable of abstraction, creativity, and wonder. The synergy between technology and imagination continues to push the boundaries of knowledge, promising new revelations about black holes, dark matter, dark energy, and perhaps the ultimate laws governing everything. Looking ahead, missions like the James Webb Space Telescope, the European Space Agency's LISA Observatory, and next-generation ground-based detectors will probe deeper into the universe's history and structure. We anticipate detecting the first seeds of black holes in the early cosmos, mapping how they grew alongside galaxies, and perhaps uncovering signatures of hitherto unknown physics deviations from general relativity, hints of extra dimensions, or the fingerprints of quantum gravity. Each new discovery will refine our story, adding fresh chapters to the cosmic narrative. Yet even as new data arrive, the core of our inquiry remains the same: to understand the universe's workings and to find our place within it. Science of Sleep invites you to join this quest not only with curiosity, but with tranquility, to let each insight be a lullaby for the mind, a gentle nudge toward restful contemplation. Just as we trace the paths of photons and gravitons across spacetime, so too can we trace the pathways of thought and reflection within ourselves. Allow your shoulders to relax fully and your breath to flow calmly as you hold these final thoughts. The universe is vast and dynamic, yet its deepest truths resonate in the stillness of your own heartbeat. Black holes, in all their power and mystery, are not distant anomalies but integral parts of the cosmic dance that brought you here. In the interplay of gravity and quantum mechanics, of jets and accretion, of light and sound, we find both the grandeur of nature and a mirror for our own inner worlds. With this reflection, let your mind drift into gentle repose, carried by the cosmic currents we have explored. May your sleep be filled with stardust dreams, each one a whisper of the universe's infinite creativity. And may you awaken with renewed wonder at the harmony between the cosmos and your own. Steady pulse, two rhythms united across space and time as your mind drifts back from cosmic vistas to the gentle comfort of your own space, if you still have the energy to leave a thought. I'd love to hear how far this little journey has carried you on. What questions linger as you drift off? Feel free to like this video and subscribe to Science of Sleep for more soothing explorations of the universe's hidden harmonies. Wishing you a peaceful night, softly cradled by stars and the steady rhythm of your own breath.